Hello everyone, my name is Anthony Schuler, and today I will be presenting a tutorial on how to perform approximate nearest neighbors classification in the R programming language using RStudio. In creating this tutorial, I had two goals in mind. First, I wanted to demonstrate with a simple example how to create an approximate nearest neighbor classifier in R, and second, I wanted to highlight how approximate nearest neighbors differs from k-nearest neighbors, and why approximate nearest neighbors can be advantageous in some situations. To create an approximate nearest neighbor classifier in R, I will be using the nn2 function contained in the ran package. According to the creators of the package, the nn2 function finds the k-nearest neighbors for every point in a given dataset in O n log n time. In this table are the various input parameters to the nn2 function along with their default values and description. Here, the data parameter represents the training data, the query parameter represents the testing data we want to make class predictions on, K is the number of nearest neighbors to search for. Tree type specifies if a k-dimensional KD or box decomposition BD tree will be used. Search type defines how the algorithm will search for the nearest neighbors, and EPS is the error bound. For this tutorial, the EPS or error parameter is the most important. Setting EPS to 0 performs standard k-nearest neighbors, whereas setting EPS greater than 0 performs approximate nearest neighbors. The next most important parameter to understand is the tree type parameter. Whether the KD or BD method is chosen, both aim to accomplish the same thing. By reorganizing the points into a space-partitioned data structure, these trees reduce the overall number of points to search through and thus decrease runtime. Note also that a fixed radius search is possible, and much like approximate nearest neighbors, can be used to decrease runtime. For this tutorial, we will be using the training set portion of the MNIST dataset found on Kaggle. This dataset contains 42,000 images of handwritten digits, numbers 1 through 9. Each image is 28 pixels wide by 28 pixels tall for 784 pixels in total. Each row in the dataset represents one image, with each column, excluding the class label column, representing one of the 784 pixels for that image. Each column then contains a grayscale value between 0 and 255 for that pixel for that image. Now that we have the appropriate software and a working dataset, let's begin the tutorial. First, we want to load the MNIST data into R using the read.table function. Here, the head function is used to show the first few rows of the data and make sure it is loaded in properly. Second, we want to split our data into training and testing sets. To do this, we will need to install and load the CA Tools package in R. Next, we can use the samples.split function to create a random stratified sampling of the data with a desired training testing split. Here, we stratify the data based on class label and perform a 70-30 training testing split. With the data loaded and split into training and testing sets, we can create our classifier. First, we need to install and load the RAN package in R. Next, we can use the nn2 function to create an approximate nearest neighbor classifier with desired parameters. For this example, we set k equal to 10, tree type equal to KD, search type equal to priority, and EPS equal to 0.99. From this function, we get two outputs. The nn.idx output contains the row indices of the k-nearest neighbors to the query point, i.e. which instances from the training set are closest to that particular instance of the testing set. The nn.dists output contains the Euclidean distances between the query point and its k-nearest neighbors. To calculate runtime, the nn2 function is surrounded by two calls of the proc.time function. The proc.time function calls on lines 31 and 34 mark the start and end of the nn2 function execution, respectively. The difference between these values provides an estimate of how long it took the nn2 function to run. Now that we know the k-nearest neighbors for each testing set instance, let's see how our classifier performs in terms of accuracy. While the code on this slide is relatively short and sweet, the logic behind this calculation is a bit more complex. For every testing instance, hence the for loop on line 39, we need to associate its k-nearest neighbor indices from the nn.idx output with their actual class labels. This is accomplished by the bit of code inside the red box on line 40. Essentially, this piece of code associates a given testing instance with the class labels of its k-nearest neighbors from the training set. Next, we need to assign a predicted class label to each testing instance. This is accomplished by the which.max function on line 40. This function acts like a majority vote and assigns the most frequently occurring class label from its k-nearest neighbors as the predicted class label of a given testing instance. Then, on line 42, we compare the predicted labels with the actual labels and calculate accuracy. Finally, a confusion matrix is created to help visualize model performance. At this point, we have successfully created an approximate nearest neighbor classifier, made predictions on a testing set, and evaluated model performance in terms of accuracy. As such, we have accomplished the first goal of this study. To accomplish the second goal of this study, I have repeated steps 3 and 4 for the parameters specified in this table. For each repetition, elapsed time and accuracy were recorded and compared across runs. Based on the table in the previous slide and the figure at the bottom of this slide, several conclusions can be drawn. First, the KD tree type produces better accuracy than the BD tree type for this dataset at least. Furthermore, runtime, i.e. elapsed time, decreases more rapidly with an increase in error for the BD tree type than the KD tree type. Next, increasing K increases runtime, whereas increasing error, i.e. the EPS parameter, decreases runtime but also decreases accuracy. In general, approximate nearest neighbors is faster than k-nearest neighbors, i.e. when error equals 0, but can result in lower accuracy. While this decrease in runtime is the main motivation for using approximate nearest neighbors, it is only noticeable with large and/or high-dimensional datasets. For example, running approximate nearest neighbors on the small iris dataset, i.e. 150 instances with 4 attributes each, is no faster than standard k-nearest neighbors. Overall, when deciding between approximate nearest neighbors and k-nearest neighbors, one needs to consider dataset size, dimensionality, and how much trade-off they are willing to accept between accuracy and runtime.